Hello everyone. If you are here on this video, you are here to watch a video on bond energy. So bond energy is a somewhat new topic to us in this thermochemistry unit. What we're going to see is that bonds, in order you want to break bonds or make bonds, you need energy. So we're going to see in a chemical reaction, when we break those bonds, how much energy is either going to be lost in an exothermic reaction or gained in an endothermic reaction. What we're going to be looking for is positive and negative values. So what you should see, or what you should have in front of you, is this current assignment. You should have the bond energies worksheet, and when you are working through this worksheet, you're going to want to click on this blue link right here. This blue link is going to take you to the constant values that we're going to be using. These constants do not change. You're just going to need to find these numbers and plug them in when you use them. So when we are doing bond energies, what we're going to do is we're going to take all the bonds. If we're looking at this reaction, we're going to take all the bonds from the first the reactants, add them together, and then we're going to subtract the product. So it's reactants minus products, R minus P. That's going to be important. When we get into a new topic later on in this unit, we're going to see a different formula, but it's just going to be flip-flop. But for now, it's reactants minus products. So this takes a little bit of review, knowing how to draw Lewis dot structures. I know it's been a while since we've done that, but we need to do that in this practice because we need to know what bonds we have. So if I'm looking at this first example, we have hydrogen gas reacting with CO2. Hydrogen is written simply as H to H. Then we're going to add CO2 to that. Remember, when we draw CO2, CO2 is carbon double bonded to two oxygens. So there are our reactants. Drawing Lewis dot structures. This is just us setting up the problem. That way we know where our bonds are. All right, then we have H2O, oxygen, bonded to two hydrogens, like so. And then we have carbon monoxide. Carbon monoxide, that one's an interesting one. That's carbon triple bonded to oxygen with lone pairs on the end. Lone pairs aren't as important as they were in the past right now. We're just looking at bonds now, but we have it set up. So now, if you clicked on that blue link, you would find a table that looks similar to this, or that is this. This is your average bond enthalpies or bond energies. As you can see within this chart, you've got all the different amounts of energy that it takes to break or form these individual bonds. So if we're looking at, for example, a carbon to hydrogen bond requires 413 kilojoules per mole of energy to produce or to break. So when we go through and look at these different things that we drew, we want to see how much energy it takes for a hydrogen bond. So I'm going to go ahead and scroll down. I'm going to look for hydrogen to hydrogen. Looks like hydrogen to hydrogen is right here. It requires 436 kilojoules of energy. Now that's in our reactant, so I'm going to put this in square brackets, and we're going to add that to how much energy we have in the bonds in CO2. Now notice there are two carbon to oxygen bonds. So I'm going to need to find what the energy is for a carbon to oxygen double bond, which I find to be 799. But since there are two of them in the equation, I need to multiply that by 2. So it's 2 times 799, and I'm going to close that all in square brackets so I know that those are my reactants. Now we're going to subtract. I'm going to move on to the products. We're going to subtract the products. So if I look at H2O, looks like I have 2 hydrogen to oxygen single bonds. So I'm going to write 2, and then I'm going to scroll down, and I'm going to see that a hydrogen to oxygen single bond has an energy of 463 kilojoules per mole. So I'm going to multiply that by 463. And then moving on, we just have a carbon triple bonded to an oxygen. So let's see what that is in the chart. Looks like a carbon triple bonded to an oxygen is 1072. So I'm going to go ahead and go back up and I'm going to write 1072. Okay. So now all we've done is we've used the chart to fill in these values. These values coincide with the values found in the chart below. We erase some of this stuff. And what we're going to now do is we're going to take the sum of the reactants and subtract the sum of the products from that. What I find works best is if you just find each individual value for each side. That way we don't need to worry about typing too much in the calculator. So for this side, 436 plus 799 multiplied by 2 comes out to be 2,034. So that's my first value. Then I'm going to subtract the sum of the products. So 2 times 463 plus 1072 is 1998. So when I take 2034, subtract 1998 from it, what I'll find is that my value comes out to be positive 36 kilojoules. So my answer is positive 36 kilojoules, which means that that is an endothermic reaction. All right. So that's basically what you're going to do in this. You're going to draw your Lewis dot structures. You're going to count the number of bonds within each Lewis dot structure. And then you're going to subtract the products from the reactants, total bond energies, to get your final energy value, which is positive 36 kilojoules, making it an endothermic reaction. So you've got 3 other examples to run through with this practice. If you have any questions, we'll have a live session on Thursday or on Tuesday, so that way you can get some help with this. It's just simple math. As long as you have that chart, you should be fine. All right, let me know if you guys have questions. Send me an email, put a comment in the comment section below. I miss every single one of you. Can't wait to see you guys again. See you later.